Hello, everyone. Come on in. Come on in. Take a seat. Don't. I don't want to do that. Anyone have any questions while we're waiting for everybody else to come in? Oh, got more people. No questions? I think I told everybody last time about the midterm, how I will automatically trade your final exam grade for the midterm grade if the final exam grade is better than the midterm. So hopefully y'all are a lot chipper now, a lot more happy. Anybody have any questions on course material? We've been through chapters 10, almost completely finished with chapter 10, but you definitely have enough to do the concept questions, which, if I'm not mistaken, are due this evening. So make sure you get them done. And then you certainly had enough to even start the mathematical and physical problems, so you can do those as well. They're not due until Sunday, so make sure you get those done as well. So no questions on anything? Okay, there it is. I don't take the highest. I take the highest for the midterm if the final's higher. So I won't do it the other way. I'm not going to give you your midterm grade for your final exam grade, because I need you guys to peak at that point, not at this point. So in some sense you're right, but yeah. So yeah, if you score better on the final, I will replace your midterm score with the final score, and that'll bring your grade up a lot. And I had a student I was working with earlier who was concerned about their grades, and their grade was in the mid 60s roughly. And I looked, and their lab grade was quite good, like 100. And comparing the two, I got basically from a mid 60 to a low, like a 74 or 73 or something like that. So remember, there is always that buffer of your lab grade if you've been attending lab every day and doing your labs on time. And then basically everybody's doing well on the lab reports themselves. So all that equates to very near 100. If you've been missing days, though, then it's going to drop down to 90s, and it's harder to pull it up, but it can help you a lot. All right, well, I guess we'll go ahead and get started. I don't have that many people here, only 10, but we got some problems to work. So last time I looked through my notes and I realized I had done some, I had worked some moment of inertia problems. So I did some integrals. I worked an integral problem where I derived the moment of inertia for a long thin rod, or rotating around its end. Then I did another one for it rotating around its center. And then I did another one for a cylinder. So those are sort of the very typical ones that you could do. You could do a hollow cylinder. You can do a sphere. A sphere is a little trickier. You gotta be kind of smart when you're doing a sphere, or you got to be willing to use a double or a triple integral. Life gets a lot easier if you can do a double or a triple integral. But anyways, that's some of the stuff you can do. I've sort of exhausted all the ways you can do it. I could actually make it a little more complicated by doing a rod and having it not be uniform. For instance, lambda could equal some constant times x to the 3 power or x to the 2 power or something like that. So that's the ways I can soup these examples up. But you should be able to do an integral to derive the center of mass or the moment of inertia of an object. So make sure you can do that. That being said, there's something called the parallel axis theorem, and then there's something called the perpendicular axis theorem. So I thought I'd give you first an example of the parallel axis theorems. So here's example 1. So let's say
on the document, Cam.
Yes, thank you for catching that. I was just catching up to it. I'm so smart. Okay. The moment of inertia for a rod rotated about its center was found to be 1/12 ml squared. What is it when rotating about the end? So the parallel axis theorem says that the moment of inertia about any point is equal to the moment of inertia about the center of mass plus m times h squared, where h is the distance from the center of mass to the actual location at which you're rotating at. So we found basically that when rotated about the center, where this is L/2 and this is negative L/2, we found that I was 1/12 ml squared. So I can see in going from the center to the end that I'm moving by a distance of L/2. So the I about the end should be equal to 1/12 ml squared plus m times L/2 squared. Really doesn't look, there you go, that looks better. Of course, this becomes L squared over 4. So I've got 1/12 ml squared plus 1/4 ml squared. I'll multiply this by 3 over 3, and I get 1/12 plus 3/12 times ml squared. And that's, of course, 4/12, and 4/12 is, of course, 1/3 ml squared, which is exactly what we got when we derived it via integration. Okay, so that's a nice, wonderful thing. And the reason why it worked is because these axes were actually parallel. So that's the parallel axis theorem that we just used there. Okay, the perpendicular axis theorem basically says that the moment of inertia about the z-axis, in other words, if it's rotating about the z-axis, it's equal to the moment of inertia about the x-axis plus the moment of inertia about the y-axis. And you can find this, I think it's on page 266. I want to show you, let me double check real quick. And that explains it a little bit more deeply. And in fact, I was telling the students earlier, I've used that exactly one time, and I think I used it that time specifically because the textbook author wanted to show that it could be used. So in this case, there's a trick though. It's only valid when the objects are two-dimensional. So for instance, a cylinder rotating, a thin cylinder, which is like a washer or a quarter or something like that, spinning about the x-axis. If you have the moment of inertia of it spinning about the x-axis and the moment of inertia of it spinning around the y-axis, then you can figure out what the moment of inertia of it spinning about the z-axis is. But it has to be like that, like a two-dimensional object. So I won't do any examples on that. I think your book might do one, but it's easy enough. And by the way, I've even used the parallel axis theorem when the axis is no longer even attached to the touching the object. So if this thing were, for instance, rotating around an axis way over here, you could even use it. So that's kind of neat. All right, now that we have that, let me do another dynamics problem, another problem where we're going to calculate the acceleration of an object. And I'm going to actually use that rod that we just worked on. So example 2 is going to be a long, thin, uniform rod. Okay. It has a length L and a mass M, and it's uniformly distributed. So what that means, uniformly distributed, means that lambda is equal to a constant. Okay. It could also mean that sigma is equal to a constant, or it could mean that rho is equal to a constant, as we talked about those before when we were dealing with the integral of r squared dm. So with that in mind, that just tells us that the moment of inertia of this thing rotating about the end, because we're going to treat this like it's a large smokestack that's been knocked over and it's going to start to fall like this. Okay, so it's basically rotating about the end. We found that was 1/3 ml squared for that moment of inertia. So I'm going to solve that problem. So what I'll imagine is that the thing has started to fall somewhat, and the angle above the horizon that it's at is the angle theta right now. And in fact, remember, an object acts like the forces on it are acting on its center of mass. So the actual torque here is coming from the weight mg acting on the center of mass, not up here, not down there, but right at the center of mass, meaning, in other words, this distance is L/2. Okay, so I'm going to draw that a little more clearly. Let's say this is theta. Let's say this from here to here is L/2. This is going to be mg. Okay, and obviously I made the angle different. That's okay. We're using an arbitrary angle, so that works just fine. What I'm going to do is use the summation of the torques is equal to I times alpha, and we're going to calculate alpha. We want to know what alpha is, and I want to know what A at the center of mass is, and I want to know what A at the top is. Okay, so that's what we're trying to solve for. Well, you can realize this is the ground, but that also makes a right triangle. Okay, and you can realize also that the lever arm vector is basically this vector right here, r. Okay, and of course this is the force vector, and you can calculate torque several ways. Torque is equal to r perpendicular times f, or it's equal to f perpendicular times r, or it's equal to r times f times the sine of whatever angles between them, not necessarily theta, by the way. That's why I wrote phi there. Okay, what I'm going to do is I'm going to take the component of r that's actually perpendicular to the force. So I'm going to use r. No, actually, I'll use f perpendicular to r. That's what I'll do. So I'm going to say torque is equal to the component of f that's perpendicular to r. And I'm going to say that's equal to, notice we can take and make r mg be a vector that points this way. That's parallel to r. And then it's another vector that points this way. That's perpendicular to r. And I'm just going to stretch my mg so it looks like those two add up to give the right vector. Okay, now you see we have a right triangle here. So this side, which is f perp, is just you can tell mg. Wait a second, let's make sure what we're doing here. So here's theta, and in this right triangle that would be 90 minus theta, and in this one right here this would actually be theta. So this one's going to be mg cosine theta. Everybody see that? And of course, F parallel would be mg sine theta, because the theta ends up here. Everybody understand how I get that theta here? So I'm going to write this as mg L/2 cosine theta. Now I'll take my torque equals I times alpha. That's going to become 1/2 mgl cosine theta is equal to, for this object we said that's 1/3 ml squared times alpha. So you can see already that the L here will cancel out with this L here, the m here will cancel out with this m here. And we can see that, in fact, A, or alpha, I should say, alpha should be equal to 3/2 of g cosine theta over L. Okay, so that's what alpha is. And notice that works from a unit standpoint too, because g is in meters per second every second, and alpha is supposed to be in like radians per second every second. And a radian is not really a unit, it's a meter divided by a meter. So in this case, you've got a meter per second divided by a meter. So that gives you just no units per second per second. Now, if you want to know the acceleration at the center of mass, well, that's just equal to, remember the equation A equals R times alpha. Well, I need to find the distance from the center of rotation to the point at which I wish to know the A. Well, that's L over 2. So I'm just going to multiply this by L over 2, and I'll get 3/4 g cosine theta, which for theta approaching 0, that's when it's just about to hit the ground. For theta approaching 0, A, center of mass, becomes 3/4 g. Whoa, I don't know why I wrote a C there. So that's an interesting thing. It's not really falling at the rate of g, and that should make some sense, because remember, this thing is being slowed down by this beam, the rest of the smokestack, if you will, up here. That's slowing it down, so it's not going to let it reach a full g, because it's got to rotate. Not only that, but there is a point somewhere along here where it'll reach g right as it hits the ground, but that's not it. So now I'm going to calculate a top. So the acceleration at the top, that occurs when the radius is a full L. So I'm going to take this 3/2 g cosine theta and multiply it by L. And for that, I just get 3/2 g cosine theta. So for theta approaching 0, then A top approaches 1.5 g. So that's often why you see, if you see a smokestack being demolished or a tall building being demolished by being pushed over, it often will break in half or break somewhere along the body of it, because these things are meant to take some lateral load. Like if they're modernly built, they're meant to take wind. Well, they're always been meant to take lateral loads, whether it be wind or earthquake or whatever. But we didn't always know exactly how best to do that, and things age over time. So they might not be made to withstand 1.5 Gs. Maybe they're only made to withstand 1.25 G or something like that, and then it would break there. In other cases, it might actually be that they're designed to handle 2 Gs laterally. I think a typical scenario is 2 to 2.5 if you're using it for earthquake design. But in this case, you see that, in fact, because of the way nature behaves as if the full force of gravity is acting on the center of the mass of the smokestack. That forces the end of the smokestack to actually fall at a rate greater than g, namely 3/2 g. So that's kind of a neat problem. Everybody understand that? Okay, so I just wanted to make sure y'all could do something like that. Now, in addition to that, actually, let me start off about writing what day this is and everything. So this is 10/27/21, and this is PHY 241N05B. That way, it's at the top of my notes when when I know it, so I can make sure I labeled it correctly. So let's look at another scenario. And to look at another scenario, I need to think about some things that we haven't addressed so far. So first off, I want to address work. I think I'll use a blue pen for this. So we remember that work was defined to be the integral of F dot dl. So what you're wanting to do is find the component of force that happens to be parallel to the motion that the object is moving in. Well, if you're talking about rotation, right, we found that the direction is in the theta hat direction, right? And we found, in fact, that dl would be like r d theta, theta hat. And then, of course, we ideally want the torque, even though we could represent it as a vector standing vertically, we could actually take the force as if it's running parallel to that, and we'd call that F perp. So what we do is we'd say, okay, well, this is going to be F perpendicular times theta hat dotted with R d theta, theta hat. Obviously, the theta hat dot theta hat becomes 1. All this stuff would be out in front of it first because of the linearity of it. And you end up getting F perpendicular times R d theta. Well, that, lo and behold, just says that work is equal to the integral of torque d theta. So that's a new equation we can make use of. It's a good equation. We are going to make use of it. Your book even numbers it. That means you can use it on your equation sheet. Speaking of which, one of our students found an equation sheet for this course, and I sent it to me. I want to send it to all you guys in PDF format as well, so y'all have it. Now, in addition to that, remember we learned that power is actually dW over dt. Well, that's kind of nice. And in fact, we were able to show that since work, or we could sort of say work is about FDL, you can sort of pretend like this dW is FDL. It's not exactly true to do that, but we still can say it. So I can say this is going to be FDL over dt. And then you just get F dot V because dl dt is velocity, right? So we had that nice expression. That's good to have. Maybe we can do something similar to it in rotational motion. And just instinctively, I would think that would mean the equivalent of force. But in rotational motion, what would that be? What's the equivalent of force regarding the force that creates rotation? You know what it's called, or the symbol we use? Oh dear, I seem to have a nervous twitch in my hand. Anybody there? Yeah, it's probably going to be torque times the rotational analog to velocity, which would be omega. So let's see. Well, P is again dW over dt. Well, what if that's just torque times d theta over dt? Oh, well, d theta over dt, I know what that is. That is equal to torque times omega. So yes, we do have an equivalent expression. It's power equals torque times angular velocity. So there's another neat little happenstance. Now we can take Newton's second law, which normally is written summation of the torque is equal to I times alpha. But if you're taking the case where you only have one torque, then you can just say torque is equal to I times alpha. And let's follow that out. Well, we know that I times alpha is I times d omega over dt. But what if omega is a function of theta? Remember the theta, the original angular measure of distance. Well, in that case, then this becomes I, and using the chain rule, we get d omega over d theta times d theta over dt. Well, that's kind of nice because d theta over dt is just omega. So I get I omega, and then times, of course, d omega over d theta. So that's another form of a differential equation we could actually use. We could say torque is equal to I omega d omega over d theta. But what I'm going to make use of it for is this. Since I know that work is equal to the integral of tau d theta, I'm going to go ahead and substitute for tau this quantity. So I'm going to say the integral of I omega times d omega over d theta times d theta. You see the d thetas cancel each other out, and that's actually these individual parts of the derivative are actual things. They're called one forms, which you'll learn about in differential forms if you ever get to take such a class. So this is actually kosher mathematics. It's not just made up crap that us physicists do. So you can cancel these two guys out in some sense. And then when you get that, you'd say, okay, well, I'm going to do the integral of I omega d omega from omega 0 to omega final. And that gives me 1/2 I omega squared minus 1/2 I omega 0 squared. And in fact, this is exactly the sort of the path I went through when I derived kinetic energy in linear motion. I basically found that the total work done was equal to the change in kinetic energy. So now we have kinetic energy being equal to 1/2 mv squared, where v is the velocity of the center of mass. And then if it's just holding still like that, and so it's just going by like this and not rotating or anything, then it's just 1/2 mv squared. But if you also have some rotational motion in it, then it's going to be 1/2 I omega squared as well, where omega is the rotation rate. And not only that, it'll have that for each axis about which it rotates. So that's our more general form of kinetic energy. So now when you write UI plus KI plus E loss, or excuse me, work in was the way I used it. Sorry about that. I always want to put E loss there. Plus work in is equal to U final plus K final plus E loss plus work out. This K final now might have to have two terms, and the K initial might have to have two terms. It might have to have mv squared, 1/2 mv squared, and a 1/2 I omega squared. Okay. So that's some of the work that we needed to do so that I can solve other types of problems. And that's going to bring me to what I'm doing next. That other type of problem is I'm going to solve a problem where, let's say a can of cheese dip is going to roll down an inclined plane, or it's going to roll down an incline, or it's going to slide down an inclined plane with zero friction. And we'll see which one will cause it to go fastest. Okay. So this is going to be example 3. So example 3, let's imagine an inclined plane. My stuff just moved as I was drawing, so it's a really ugly inclined plane. That's going to be an angle theta. And I'm going to have an object of radius r and mass m, and it's going to be a cylinder. Okay. So this is a cylinder, uniform cylinder. And since I chose to do cheese soup or cheese dip, you know the thickness of that stuff is going to require that the cheese rotate along with the can when it's rolling. Whereas if I did just like a chicken noodle soup, the liquid pretty much sits still for a long period of, or for a certain period of time as the can rotated around it. I don't want that. I want the whole mass to be rotating for it to make sense. Okay. So I would like to know, what is V final if A, it slides without friction, and B, what if it rolls without slipping? Okay, so I'm trying to find the final velocity in both scenarios. So let's find the final velocity. What I'm going to use is conservation of energy. I'm going to say UI plus KI plus work in is equal to U final plus K final plus E loss plus work out. And in this case, I'm going to assume there's really no loss in any of these extra energies. So I'm going to call that 0. I'm going to call that 0. And I'm going to call that 0. Not only that, it's rolling from rest. So the initial kinetic energy will be 0. And it's going to come to a stop at what I consider the 0 of potential energy. So that'll be 0. So we've made the problem a lot simpler already. And in fact, all we have is assuming we know the height h, which we do, okay, we can say m times g times h. Now, you might bicker that it's actually h plus r, and that would be fine. But I could also say, well, I'm just going to call the height h because it's going to go from a height of h plus, some fraction of r down to a height of 0 plus that same fraction of r. So that's why it's okay to just call it h. So I got mgh is equal to that. Now I've got the, in the first case, part A, we have that it slides without friction. Okay, sliding without friction means that it's not going to rotate at all. So all I have is 1/2 mv final squared as my total kinetic energy at the end. Oh, that's supposed to be the same m, by the way. I try to use a capital M to separate from just formulas to try to make a distinct thing. So anyways, we see that that's independent of mass because the mass can cancel out on both sides. So I end up getting V final is equal to the square root of 2gh. Okay. So that's how fast it will be going at the bottom. Now in case B, rolling without slipping means that V has got to equal R times omega. Okay. Remember that came from S is equal to R times theta. And if you take the derivative of that, you get V equals R omega. And that has to be true if there's no slipping. The S equals R theta has to be true with no slipping, because otherwise you would go a different distance than R theta. If it was, for instance, spinning out, then R times theta would be a lot larger than S. But if R times theta is exactly equal to S, that's rolling without slipping. And taking the derivative of that, I get V equals R omega. That's the same thing as rolling without slipping. So now I'm going to do the same thing. I'm going to get M. Dang it, keep writing the wrong M. I get big M GH is equal to 1/2 big M V final squared plus 1/2 of I omega squared. Remember, we learned I omega squared is the kinetic energy due to rotation. But since this is a cylinder, I know that I is 1/2 ml squared. And then, of course, times omega squared, because remember, it's 1/2 I omega squared. So I'll put omega squared here. Now, because of that, I can see I've got an L squared and an omega squared. I said L. Why did I say L? I have an R squared and an omega squared right here. And R omega is in fact V. So this quantity right here is V final squared as well if it's rolling without slipping. I also see that my masses can cancel out, which is good. You wouldn't want it to depend on mass in this scenario, but not in the other. So in this case, I end up getting G times H is equal to 1/2 plus, notice this is 1/4 V final squared. Okay. So that's going to give me 3/4 V final squared. So ultimately, I see that V final would equal the square root of 4/3 GH. And that means that, in fact, rolling without slipping is actually slower than sliding without friction, because 4/3 is greater than 2. Actually, why did I say that? 4/3 is less than 2. I changed my mind about which order I was writing it in the middle of it. So I changed the wording there. So yeah, because 4/3 is less than 2, we see that V final for this one is slower. And that should make some sense because some of the energy of the system, namely mgh was its initial energy, some of that energy had to go to increasing the kinetic energy of the center of mass, but then another part went to increasing the kinetic energy about the center of mass. So you had to divvy up the velocities over two different modes, hence you got a slower speed. That means in a race, sliding without friction would lose to rolling without sliding, without slipping. Any questions on that? All right, so let's do another example. Let's do example 4. What I want to do with example 4 is I would like to determine the minimum coefficient of static friction required to have something roll without slipping. Okay, so I want what coefficient of friction is sufficient for causing a cylinder to roll without slipping. Okay, so that's my big question. And all I have to do to solve this is basically imagine a cylinder on an inclined plane like this. Okay. Now, what I know is going to happen is I'm going to create a coordinate system tilted along with the axis. So I'm going to have a positive x-axis going this way, x prime axis say, and a positive y prime axis going that way. So when I do the free body diagram of this, I'm basically going to have, actually, let me use blue. I'm going to have so the forces acting on it are going to be its weight, mg, and then it's also going to have a force in the negative direction along the x-axis. That is the friction force, which is mu times the normal force. Then it's going to have a normal force acting on it, which is right there. And then I have to break this mg, which, by the way, notice this angle is theta, because that's the incline of the actual inclined plane. So since that's theta, you can see that this angle right here will also be theta. The reason why you know that is because this angle right here would have to be theta. So this is 90 minus theta. So this must be theta as well. Okay. That means also that I can take mg and apply it in the negative y direction as well as in the positive x direction. Okay. This one, of course, is going to be mg sine theta. And this one's going to be mg cosine theta. So if I take my summation of forces in the y direction equals mass times acceleration in the y prime direction, we can see that the object's not supposed to be bouncing up and down on the incline. So this quantity is going to be 0. That's going to, in fact, give me F normal minus mg cosine theta is equal to 0. So that tells me that F normal is, in fact, mg cosine theta, which we already knew that. We've had enough experience doing that. Now I take the summation of forces in the x prime direction is equal to mass times acceleration in the x prime direction. That's going to give me mg sine theta minus mu. Now remember, we figured out that mu friction was mu times Fn, and we figured out Fn was mg cosine theta. So I'll write mg cosine theta, and that's all equal to m times the acceleration down the incline. All right, so that's a useful equation as well. Now I will ask you this. I'm asking what coefficient of friction, and I mean that in two ways. One, I'm going to calculate the value in a second, but two, is this kinetic friction or is this static friction? Can anybody tell me?
Static.
Yes, it's static, because the since it's rolling without slipping, the ball cannot be rolling and moving relative to the surface. Now I've got the summation of the torques is equal to I times alpha, and rolling without slipping, of course, requires alpha to be A over R, or you can say A to be R times alpha. So with that in mind, I can see right now that the only, notice this weight is actually acting right on the center of mass. So it has no lever arm. It's rotating about the center of mass. So the center of rotation is the center of mass. And since the mg is acting along that and the Fn is acting along that, neither one of those cause an actual torque. It's only this friction force that's causing a torque. So I'm going to say that the friction force times R is the only torque we're dealing with, and that's got to be equal to 1/2 m r squared times alpha. Again, we see that one of those r's cancels out like we've seen in previous things, and now we've got r times alpha right here. That's actually A. So this allows us to solve for A. A is going to equal actually, you can use it to solve for friction, or you can use it to solve for A, whatever you want, doesn't really matter. Actually, yeah, I'll go ahead and solve it for friction. So that part's A. I'm going to say that friction is going to be equal to 1/2 m times A. And of course, I can plug this back in here into that expression, mu mg cosine theta, and that would allow me to determine mu, but in terms of A. Notice the m's cancel out as well. So let me go to the next page to get what I'm to fit the actual work in. So I'll take another sheet of paper. Got lots of pens falling all over the place here. So refreshing what I already know, I had found that F is equal to 1/2 ma. Okay, and that has the right units. The friction force should have units of force. M times A definitely has units of force. That also means that the friction force, which is mu times the normal force, is mg cosine theta. So in principle, you could say, well, mu is obviously equal to, notice the m's cancel out, and you get mu is equal to A over 2g cosine theta. but that's not very helpful because that's in terms of A. So why do that? Well, we still have this equation right here, which says mg sine theta minus mu mg cosine theta is equal to ma. We could cancel all those m's for starters. And now we could go ahead and plug this in and solve for A if we want, or we could even go back to the original scenario and just write F here and substitute in for that. So for instance, we could say, wait a second, this is just F. And I just found earlier that F was 1/2 MA. So let's do that just for the heck of it. When I do that, I get G. Well, actually, I can't cancel out the m's if I do this. So I'll say mg sine theta minus 1/2 MA is equal to MA. So see how I just took that equation right there and substituted this in, substituted F in for that. So now I can pull that to this side, and now I've got all my m's everywhere. And I'd see that G sine theta is actually equal to, when I pull this over here, this becomes 3/2 A, because it's 2/2 plus 1/2. So finally, I find that A, the acceleration of this thing, will be 2/3 G sine theta. So that's something we didn't ask for, but it's a result now that we have. I can tell what the acceleration is, and we can tell that the acceleration is constant, because as long as the incline is not changing the steepness, then this is a constant. But now that we have that, we can go back and say, well, F was supposed to be equal to 1/2 MA. So F was equal to 1/2 M times A. Now becomes 1/2 M times 2/3 G sine theta. Okay. So when I do that, I can see the 2 down here cancels out with the 2 in here. The M cancels out with this. And lo and behold, I get F, the whole force now, not the coefficient of friction, is in fact 1/3 G sine theta. Now that's also equal to that's also equal to mu times mg cosine theta. Remember, it's mu times the normal force. So now I can solve for mu. So mu, which is what we were asked for in the beginning, is going to be 1/3 G sine theta over mg cosine theta. And did I do that? Is that okay to have that in there anymore? Let's see, F is equal to, oh yeah, I shouldn't have done that. This M still has to be there, by the way, folks. Notice F was 1/2 MA. When I equated these two, I could factor them out, but that's not something I should have done, because I'm not using this equality, I'm using this equality. Okay, so this has to be 1/3 mg sine theta. And then divide that by cosine theta, and you'll get a often used result, but it's got an extra little factor in it. Mu has to equal 1/3 tangent theta. And that's for a cylinder. Any questions on that? Now, since that A is constant, that means all our equations are at our disposal. I can say, for instance, the distance along the plane that it slides, x, is equal to 1/2 AT squared plus V0t plus the initial position, because that was the equation that required the acceleration to be a constant. And since it's a level, it's a steep slope, but since the line is straight, the theta is a constant. So all this is a constant. You can also use V squared is equal to V0 squared plus 2a x minus x0. All those equations are valid, and we can ask all sorts of neat new questions. But that's basically it. That's the entirety of the chapter 10 on rotational motion. Our next chapter that we're covering is actually going to be special relativity, and then we're going to go back and cover chapter 11. After that, we'll jump back or we'll jump ahead and cover chapter 14 and then 15. So just telling you where we're going, so you'll know, the assignments that are up there for chapters that we haven't covered yet, the dates don't mean anything. So for instance, chapter 14 and stuff like that is irrelevant right now. Anybody have any questions on how that problem was solved? Okay. Well, I got about 25 minutes here, so I'm going to go ahead and start into chapter 36, unless anybody can think of something else they need help with on chapter 10. Okay. So this is chapter 36, special relativity. Okay. So let's stop for a second and y'all can look at me. So what we're going to talk about now is special relativity. Now, special, we often use to mean like really, really good, really, I made a special gift for you. Like that's really great, right? In relativity, we have special relativity, and then we have general relativity. And special means something very special, but it means it in a weak way. It means it's special in that it only covers a certain class of problems. So special relativity was an attempt of Einstein to make sense of the world without considering gravity. Now that seems really weird, but that's what he had to do, because what was going on is we had Maxwell's four equations by this time had become in the vogue, and everybody had understood that these equations were right and they're awesome and all that good stuff. Poor Maxwell didn't have that luxury when he was alive, because he died shortly thereafter of a horrible case of stomach cancer, just like his mother before him. Really terrible case. But some guys called the Maxwellians basically made Maxwell famous by, for starters, Oliver Heaviside, who was a person that wasn't wealthy enough to go to college, but he did take the national test, and at sixth grade basically beat all but like 2 or 3 people at the 12th grade level. So he was a brilliant man, but he was just too poor, so he couldn't do anything. He got into the telephony business, which was basically the predecessor. Telephony, it'd be telephone, but it's actually a telegram industry, where we were making Morse code, and he was working on running a line across the ocean between Great Britain and America. And he got that job because his sister was married to a rather famous physicist by the name of Wheatstone. You've heard of the Wheatstone Bridge, maybe, but that guy was pretty famous. Anyway, so he got this job, and he turned out to be a real ringer because he was actually a mathematical genius. I mean, he invented various things of mathematics that we use to this day. You could argue that him and an American are solely responsible for creating all of vector calculus. So what he did was he read Maxwell's book and then translated that from the quaternion and just the written language that Maxwell had created. He put that in vector calculus form. And in doing so, he made it where everybody could get it, because he was teaching people how to do the vector calculus as well as teaching them what vector calculus was. And nobody had taken really the time to learn quaternions. That was something created by a guy by the name of Hamilton. Not that Hamilton, but a very famous physics and mathematics Hamilton. And he made the Maxwell equations super famous and somewhat easily understandable. And we teach them now in 242, where you do both the differential form and the integral form, and you learn quite a bit about them. So that was unheard of back in that time. But by the time Einstein's on the scene, so that was like 1865-ish, was when Maxwell put his stuff out. By 1905, when Einstein has this famous year where he wrote basically 7 papers, all of which could have won him the Nobel Prize, by that time, electricity and magnetism and physics in general had learned that electricity and magnetism was Maxwell's equations. So Einstein looked at Maxwell's equations, and if you play with Maxwell's equations in a very special way, you can get an equation that is what we call a wave equation. Now, a wave equation has a very specific form, which you'll see in chapter, I think, 15. But basically what it is the second order derivative in space. Let's say that. Yeah, second order derivative of something in space is equal to 1 over some quantity squared times the second order derivative in time. Now that quantity squared in there tells you about the velocity of the wave. Okay. Now here's the weird thing. When Maxwell did that with his equations, there was a quantity in that slot for velocity that was, one of them was related to the ability to magnetize matter, and the other one was the ability to charge matter. And neither of those seemed reasonably to be related to one another, and they certainly didn't seem to have anything to do with electricity or magnetism or light. But lo and behold, when you multiply those two numbers and then flip them over and take the square root, which is what the velocity requires you to do to calculate, you found that the velocity was exactly the speed of light. So at that instant, Maxwell knew what light was. It was these electric waves oscillating in one plane, and then perpendicular to that is a magnetic wave, and then perpendicular to both of those is the direction that it goes, the velocity. So having that equation was kind of weird, because Einstein looked at it and realized if you switch to a frame of reference that's, say, moving at half the speed of light, you still get the exact same wave equation. If you switch to a frame of reference that's moving the opposite direction at 99.99% of the speed of light, you still get the exact same equation. And because of that, he was picturing all these crazy paradoxes, like you wouldn't be able to see your own image, you could turn back time, all sorts of weird stuff like that. And I just made that turning back time thing. But that was the big problem. So many people say a genius is the person that can hit a target that no one else can hit. A better definition of genius, in my estimation, and one I learned from a book I was reading on the Great American University, is a genius is the person that sees a target that no one else has seen and hits it. And that's what Einstein did. Einstein had no experiments suggesting anything was wrong. Einstein had no data suggesting physics was jacked up. All Einstein had was his imagination and the laws of what he thought God was, which is a Spinoza idea of God, thinking through the process of applying this equation in weird scenarios. Gedanken, thought experiments is what he called them, Gedanken. And when he did that, he kept finding paradoxes, and paradoxes are an anathema to physics and science in general. You can't have two things both be valid and point to conflicting results and have a robust science. So by that alone, he just decided to write this paper, and it was called On the Electrodynamics of Moving Bodies. And that's kind of weird, because why do you do electrodynamics? Well, because it came from electricity and magnetism. So what he did in order to fix this was he said, the only way this makes any sense is something absurd. The first thing is the special principle of relativity. And he said the laws of physics are the same for all inertial observers. That's special relativity principle 1. Your book says it. You can write it now if you'd like. I definitely suggest you memorize it. So the first principle of special relativity is the laws of physics are the same for all inertial observers. Inertial, I-N-E-R-T-I-A-L. observers. Okay, what do we mean by that? Well, remember when we talked about Galileo discovering that it was as if something has inertia, a reluctance to change its velocity, a reluctance to change its speed or direction, in other words. That later became Newton's first law of motion. But if you think about it in terms of inertia, like Galileo phrased it to make people feel better about turning their back on Aristotle, then it makes a little bit more sense. What he's saying is, whenever you look at a system and the system appears to be violating Galileo's principle of inertia, then that is a non-inertial frame. So one example would be, you take a merry-go-round on a playground, the little thing you run beside or whatever, you get it spinning, right? And before you do that, you've actually attached a camera up over the spinning thing, and the camera shows just the spinning disc, but it's attached to the spinning disc, so you can't tell the disc is rotating. You only see the disc, you don't see the ground around the outside. Well, if you happen to have stuck a basketball right there, pretty much dead center, doesn't really matter if you get it right on the money or not, it's still going to happen. And then you spin the ball, spin the merry-go-round. What it'll look like from the camera is that this ball was sitting there, and for no reason it accelerated out the side of the frame. Okay, you cannot visually see a force acting on that object, so you would conclude that that was a non-inertial reference frame because something accelerated without a force acting on it. Remember, an object in motion tends to stay in that state of motion unless acted upon by a net external force. There was no obvious net external force, yet it did change its motion, it accelerated. So that's a non-inertial frame. Now, the bigger idea, and this is what he was really shooting at, is when you go back up high above the sun and our solar system and look back down, you don't see any ropes attaching the sun to Mercury or Venus or Earth or Mars or Jupiter or the moon to the Earth. You don't see an obvious force doing that. Yet you see objects, the planets, changing their motion. They're going in elliptical orbits as opposed to straight lines. They're speeding up and slowing down. That's a non-inertial frame. So Einstein's saying, wait a second, there's no reason to assume gravity is a force. We're just in a non-inertial frame. So him calling it special relativity meant we considered, like Jared suggested, the specialized case in which there is no things accelerated unless an obvious force is acting on it. So he's getting rid of that idea of action at a distance by saying, I'm not going to acknowledge that gravity is a force. I'm just going to acknowledge that right now the laws of physics suggest that the universe may be in a non-inertial reference frame. Okay, so when he says the laws of physics are the same for all inertial observers, that just means, hey, I'm getting ready to write some crap down, and this crap is going to be applied everywhere except where you call gravity's going on. Okay, or except where you see things shooting off of merry-go-rounds and don't realize the merry-go-round's rotating. Okay, then the second law is actually really the simpler one, but it's the most absurd. And the second one is that the speed of light is a constant independent of the motion of the source or the motion of the observer. So the speed of light is a constant independent of the motion of the source or the motion of the observer. The speed of light is a constant independent of the motion of the source or the motion of the observer. What do we mean by that? Well, you know for a fact, as we covered in Galilean relativity in like chapter 2, I think it was, if I'm riding on the back of a flatbed truck trailer at 60 miles per hour, and I stand up with my old arthritic shoulder and throw at a whopping 40 miles per hour, because that's probably all I got in me now, throw a ball in the same direction the Mack truck's going, then 60 plus 40 is how fast you sitting on the side of the road will think that ball is coming toward them or toward you, right? Because basically, if the ball was allowed to travel for a whole hour, then what would happen if the ball, the truck, and everything was allowed to travel for a whole hour without gravity pulling it down and weird stuff like that? Then what you'd see is the ball would move 40 miles beyond the point where it left my hand on the truck. But then in addition to that, that point on the truck will have moved 60 miles past where it was on the road. So the total distance the ball traveled was 60 plus 40, which equals 100. So that's why the velocities added and gave me 100 miles per hour. And that we've worked out that over and over again. It's simple. We know it for a fact. The problem is if I throw a ball at the speed of light, then all bets are off. Okay. If I throw it at the speed of light, it doesn't go the speed of light plus 60. It just goes the speed of light. If that Mack truck happens to be going half the speed of light, and then I shoot a photon beam or a photon the same direction as the truck's going, the photon beam, according to you on the side of the road, will be traveling at you not at 1.5 times the speed of light, but at exactly the speed of light. And then me, I will measure it with a radar gun and it'll say, dang, that's going the speed of light. The speed of light is 299,792,458 meters per second. That's really fast. 299,792,458 meters per second. That's basically 8 trips around the equator in a single second. Okay, so that's really, really fast. It's almost the whole distance to the moon in a single second. Okay, so that's the speed of light. And everything in that area going roughly that speed. So once you start to get dealing with 10% the speed of light, or even 1% the speed of light, if you're carrying it to enough decimal places, when you start doing that, then you have to start taking into account relativity. But the weirdness is the ramifications of this. Notice I said that you would see my photons moving at the speed of light, even though you're on the side of the road and I'm on the back of a Mack truck. Let's say this time I'm going 99.9% of the speed of light, the Mack truck is, and then I shoot the photon torpedo. You do not measure the photon coming at you at 1.999. You measure it again at exactly 1 times the speed of light. And I still measure it at exactly 1 times the speed of light. That is that weird second principle of relativity. Okay, now you might think, what's that got to do with anything? Well, let me show you what Einstein did. It's brilliant. It's another one of his Gedanken. So I'm going to turn on my document cam again. And what we can do is we can imagine a train car. And this is actually what he did. And he has a book called The Principle of Relativity. Well, actually, that one's kind of bad, but he's got another one. I forget what it's called, but it's a layman's book, and it actually explains it to you as best he can without math and all that stuff. But it's not very good. It's much better to read, Hawking's book or Brian Greene's book or something like that. But we're gonna have to imagine a scenario and make it involve light so that he can apply this principle of relativity. So what he did was he imagined a timepiece that was made using light. And it's perfectly reasonable. Basically, what you imagine is a little flashlight right here that shoots a beam of light up, and then that hits a mirror and the beam of light shoots back. And when it gets back, that's 1 click of time. So if this distance from here to here was a light year, then it would take 2 years for it to have 1 click. If, however, it was a half a light second, then it'd take 1 second to go up and back. Okay, but that's his timepiece. Okay, and you have an observer that is on the train riding with the clock, and then you have another observer on the side of the train track watching all this go on. So let's call this distance right here, let's call that distance just plain d. Okay, and let's say the train is actually moving at a velocity v. So I'm going to look at it a little time later, and what I'm going to see from the side of the track is that this light beam, which person in the vehicle says is going straight up and straight down, this light beam from the side of the track actually went up and to the right. And then a little time later, the train is over here, and that beam of light has now gone from here down to here. Okay, so you see how we're seeing 2 different scenarios. From a person on the train standpoint, they just see the beam go up and down. So they would say, let's say on the train, they would say that delta t0, I'm going to put a 0 on there for reasons that'll come clear later. Delta t0 is going to be equal to distance divided by velocity. So the distance is 2d and the velocity is c. Okay. On the bank, it's going to be a little different. On the hill next to the track, say. That time, delta t, is going to be this distance divided by c. Okay. Well, this distance, notice, is from here to here is basically 2 times the velocity, or excuse me, it's basically velocity of the train times delta t. Okay, this would be in fact half of the velocity of the train. I'll write it right here. This would be half the velocity of the train times t, and then this would be d. So we can see the distance traveled, at least from here to here, is going to be the square root of d squared plus v delta t over 2 squared. That's the distance, one of those. So the other one should be the same length. So I'll put a 2 in front of that, and then I'll put the speed as c here. Now, in reality, if we were still in Galilean relativity, the speed would not be c. It would have been c plus v, right? Or c plus some fraction of v because it's at an angle, but still it just wouldn't be c. But in relativity, we're forced to say that's the same speed. Okay. So we can now say that this is going to be the result. What I can do is square this, and I'll say delta t0 squared is equal to 4d squared over c squared. And then I can square this and say delta t squared is equal to 4d squared plus v squared delta t squared over 4. All that divided by c squared. Okay. Now, if I distribute this 4 in here, I get 4d squared. And if I pull the c squared under there, I get 4d squared over c squared. And then I do the same thing over here. I get 4 over 4 times v squared delta t squared over c squared. Okay. Well, lo and behold, this right here is delta t0. So I can now say delta t squared is actually equal to delta t0 squared plus v over c squared delta t squared. I can pull this delta t over here and then factor it out. So I have delta t squared times 1 minus v over c squared. I'll put that in square brackets, is equal to delta t0 squared. And now finally, I can say that delta t, the time that the person on the bank measures, delta t is equal to delta t0. Notice I've taken the square root of everything, divided by the square root of 1 minus v over c squared. Now, this is often written gamma times delta t0, where gamma is defined to be 1 over the square root of 1 minus v squared over c squared. Now, gamma is also often written 1 over the square root of 1 minus beta squared, where beta is defined to be v over c. So all of those are some different notations you'll use. But this is called the proper time. That delta t0 is called the proper time. And it's not proper like meaning correct and all of the times are wrong. It's more from the German version. But basically what it means is this is the time that's measured with the timepiece not moving. Okay. So if you want to measure time, you should measure time by a clock that you're wearing or that's sitting still next to you. If you do that, then you get the proper time. Now, since v is always going to be less than c, then you're always going to take 1 minus something less than 1. That means this whole quantity is going to be less than 1. And you're going to take the square root of it. That's still going to be less than 1. And then you're going to divide this by that. That means this is going to get bigger. When you divide delta t0 by this quantity, you're going to get a bigger number than delta t0. And that means we're experiencing time dilation. Moving clocks run slowly. And the relativity of this is that basically, hey, if I look at your clock as you ride by me in a car going, 3/4 of the speed of light, I'll look at your clock, and your clock, instead of the second hand moving like this, your second hand will be going. Now, here's the weird part. If you look back at me from your car, you'll see me whiz by you, and you'll see my second hand going. And you're both right. Okay. We're both right. I'm right in seeing your clock go slow. You're right in seeing my clock go slow. And there's no contradiction there. It seems like there is, but there's no contradiction there whatsoever. So that's our first big conclusion from relativity. And that all came from those two principles of physics. The laws of physics are the same for all inertial observers. And that actually just speaks to the formalism that we're going to have to use, meaning the laws of physics should all have the same form no matter what reference frame you're in. So that means they should take a tensor form, because tensors are things that can be translated into other coordinate systems and still have the same form. So if it's linear, it's going to be linear there. If it's quadratic, it's going to be quadratic there, so on and so forth. And that helps us with the general relativity part. The other part is the speed of light is a constant independent of the motion of the source and the observer. And we've seen already how that gets us an actual time dilation equation. What I would do if I was you is, find all the values of beta, V over C. Beta is like 20%, 0.2, that means 20% of the speed of light. Find all the values of beta that makes gamma equal to a whole number like 2, 3, 4, 5, 6, 7, 8, 9, 10, 100, 1,000, 1,000,000, stuff like that. Because that gamma factor is the important thing. If I go, for instance, a speed at which the gamma factor is a factor of 10, then I can travel, let's say, 10 light years away. And because I'm going so fast, where the gamma factor is 10, it'll only take me about 1 year to get there, according to my clock. Because this time dilation factor fixes it. Okay. Now we'll learn that there's a length contraction as well, and we'll learn a bunch of other stuff. But we're out of time. You guys are free to go. I'm waiting. Remember, you got homework due tonight. Conceptual homework for chapter 10 is due tonight. We've now started chapter 33, so I've got to set the dates properly for chapter 36. Excuse me, I said 33. So I've got to set the dates properly, but I think I might have already done that. You folks are free to go. Thanks for coming.
I had a question.
Yes.
I was confused on some of the earlier stuff, and I was trying to find the sections on the Canvas page, but it looks like Canvas is only updated to chapter 6.
Oh yeah, that's when I basically, it was taking me too many hours to put the videos on the individual Canvas page, so I told everybody to just go to my YouTube channel. And I started updating that list on my YouTube channel as well. So if you look in the YouTube channel, let me share my screen with you real quick. I'm going to go right here, and then I'm going to open another window, and I'm going to put up my YouTube channel, and then I'm going to click on that window. Okay, so if you look on these, you'll see that the actual date and class is written in it. So there's PHY 241 D01C. That's my Tuesday morning class. And that's from October 26, 2021. If you go back and look at this one, you can see that again is my Tuesday class. That's because the first time it went up, it failed, so I had to redo it. But that's again my Tuesday class, but that's from October 21st. Let me show you another one, because you probably want one that says DO1B. If you have a bigger screen, hopefully it'll show it better for you. This is one where I just showed the Atwood machine on 1025, but it was for a Physics 241 class, but I just did it. It wasn't an actual class lecture. It was me teaching. And let's see right here. So if you just keep looking in these individual parts, you'll see that each one of them has the class and what day it is. So D01B, that's my morning, Monday, and Wednesday classes, our Monday, Wednesday, and Friday classes. That was from 10:25. And I keep them up every day. Like I normally can post it the same day. Sometimes it takes a second day to do it. There's the other DO1B. All yours are up here as well. I just haven't hit one yet, like a crackhead. Conservation of energy. This is probably it. Let's see. Darn it, another DO1C. What the heck? No, that's 242. I don't want that one. So maybe this is one. Chapter 9 boat. That's where I made a correction. I had a lot of extra videos I made, so it might be something related to that. There's a DO1B. Where are all my N05Bs? Maybe I haven't been putting them up there. I will. These are all the same material though, so you can still look at them. It's just I was looking for an N05B. It looks like you might be onto something. I might have neglected to put these up. I haven't seen an N05B yet. That's frustrating. That can't be it. That's 242. I did find one time that I'd put one up as a 241, but it was actually a 242, so that's not very good. That's another D01C. I will address that, but until then, you can look for what material is being covered. Basically, we were covering the same material same days. So if you look at D01C on the day after your class, that will be the same material you covered in your class for a particular day. So until I get the other N05s up, which I don't know why they're not up, then do that. Sorry about that. That's really a big bad screw up on my behalf. I didn't know I did that at all. But thanks for calling it to my attention. Who was that asked? Was that Jarrett?
Yeah, that was me.
Okay. Yeah, Jarrett. So look at the D01Cs. The D01Bs are nice too, but they're only 50 minutes long. So I usually have a little mix up between what we're covering in that one versus what you're covering in your class. But the D01C and N05 covered the same thing, except you covered on Monday, they covered on Tuesday. And then you cover it on Wednesday and they cover it on Thursday. Okay.
All right.
Sorry about
Thank you.
that. I will address that as quickly as I can. It seems like I do not have any N05s up in the last 10 days.
Thank you.
You're welcome. Anybody else have any questions? All right. Well, I guess I'll call it a day.
Professor Young,
Yes, sir.
I wanted to speak to you in a
Private.
breakout room.
Okay, let me